300 rads in 1 hour will kill a human being, not eventually, not over years, in 1 hour. Now consider this. The surface of Europa, one of Jupiter's moons, delivers between 500 and 400 rads every single hour. That means standing on Europa, you would absorb a lethal radiation dose before the hour was up, possibly in minutes, depending on where you stood, and Europa is not even close to the most dangerous place in Jupiter's system. There is something nobody really talks about when people dream about visiting Jupiter, something beyond the radiation, beyond the pressure, beyond the storms. We will get to it. But first, let us understand exactly what kind of place Jupiter really is. From Earth, Jupiter looks almost peaceful. Those smooth bands of orange and cream, the swirling clouds, the iconic red storm sitting in the southern hemisphere like a permanent bruise. On a clear night, it is one of the brightest objects in the sky, steady and calm, nothing like the chaos happening on its surface. But that calm appearance is a lie. Jupiter is the most hostile environment a human being could attempt to reach anywhere in our solar system. Not because of one single danger, but because it layers danger on top of danger on top of danger, so that even if you survived one, the next would finish the job. Today we're going to go through each layer, from the moment you leave Earth, through the radiation belts, into the atmosphere, down toward a core that nobody fully understands yet, and by the time we're done, you will understand not just why no human has ever gone to Jupiter, but why sending a robot there is already considered one of the most difficult engineering challenges in the history of space exploration. Jupiter sits roughly 600 million kilometers from Earth on average. That distance alone is a problem. Even at the speeds our fastest spacecraft can achieve, getting there takes over a year. During that entire journey, you are outside Earth's protective atmosphere and magnetic field, exposed directly to the stream of charged particles constantly flowing from the Sun. Scientists estimate a round trip to Mars, which is less than half the distance to Jupiter, already pushes an astronaut close to their entire lifetime safe radiation limit. By the time you were approaching Jupiter, you would already be running low on the radiation budget your body can absorb before the risk of cancer and organ damage becomes critical, and that is before Jupiter even comes into view. Because Jupiter does not wait for you to arrive before it starts trying to kill you. Jupiter has the largest and most powerful magnetic field of any planet in the solar system, roughly 14 times stronger than Earth's. Its magnetosphere, the region of space dominated by that field, stretches 20 million kilometers in every direction. That is so large that if you could see it from Earth with the naked eye, it would appear several times wider than the full moon in the night sky. That magnetic field is what creates Jupiter's radiation belts. Think of them like two enormous rings of charged particles, electrons, protons, heavier ions, all trapped by the magnetic field and accelerating to extraordinary speeds as they circle the planet. Earth has its own version of this, the Van Allen belts. The Apollo astronauts passed through them on the way to the moon, spending roughly an hour in transit each way, carefully shielded. Total radiation exposure was survivable. Jupiter's radiation belts are in a different category entirely. In the most intense zones, the dose rate runs into hundreds, sometimes thousands of rads per hour. Some of Jupiter's inner belt regions deliver energy so high that the protons can punch through substantial metal shielding. Engineers at the European Space Agency, planning the JUICE mission to Jupiter, call the radiation environment a clear and present danger, and they are designing a robot, not a crewed spacecraft. For a human being, the maths is simple and brutal. 300 rads delivered in under an hour is a lethal acute radiation dose. Jupiter's inner belts deliver that and more. The astronaut inside would not feel it happening. Radiation poisoning does not announce itself. But within hours, the damage to DNA, to the digestive lining, to bone marrow would begin. Within days, unsurvivable. The Juno spacecraft has been orbiting Jupiter since 2016. To protect it, NASA built a special vault made of titanium around its most sensitive computers. Even with that protection, radiation steadily degrades Juno's systems over time. Scientists race to get data before each instrument fails. Juno is built specifically to survive Jupiter's radiation. It is a machine. It has no pain, no biology, no cells to destroy. And even Juno is slowly being killed. Of all Jupiter's moons, Europa gets the most attention, and for good reason. Beneath its cracked shell of ice, which can be several kilometers thick, Europa has a liquid saltwater ocean. Scientists estimate that ocean is between 40 and 100 miles deep. More importantly, it contains more than twice as much liquid water as all of Earth's oceans combined. Given what we know about life on Earth, that it can survive in almost any environment as long as liquid water is present, Europa has become one of the most compelling places in the solar system to search for signs of life beyond our planet. In October 2024, NASA launched the Europa Clipper, a $5.2 billion spacecraft specifically designed to study Europa. It is already proving its instruments work. In November 2025, still in deep space, it used its ultraviolet spectrograph to observe an interstellar comet passing through our solar system. Its subsurface radar was confirmed operational at Mars in August 2025. It will arrive at the Jupiter system in April 2030 to begin 49 carefully planned flybys of the Moon. Notice what Europa Clipper is not doing. It is not landing. It is not orbiting Europa for months at a time. It is flying past, dipping into Europa's environment and pulling away as fast as its trajectory allows, because even this spacecraft, built with a radiation vault made of gold-plated aluminium designed to absorb the worst of the particle bombardment, cannot survive long-term exposure to Europa's radiation environment. On Europa's surface, unshielded, the dose rate is between 500 and 1400 rads per hour. A human standing there would be dead within the hour. The ice might protect what is below, but the surface itself is a killing field of invisible particles. And here is what makes that even more significant. In January 2026, scientists reanalyzing data from NASA's Galileo spacecraft found something hidden in decades-old readings: ammonia-bearing compounds on Europa's surface. Ammonia contains nitrogen, one of the 4 building blocks of life as we know it. It was the first detection of nitrogen-bearing compounds at Europa ever, and the location where they appeared matters, concentrated along fractures in the ice, precisely the places where liquid from the subsurface ocean would be expected to push upward. The ocean below may not just exist, it may be actively moving. Now move past the moons, move past the radiation belts, move toward Jupiter itself. As you descended into Jupiter's upper atmosphere, the first thing you would notice is that there is nothing to land on. Jupiter is what astronomers call a gas giant. There is no surface, no ground, no floor, just atmosphere, getting thicker and hotter and more crushing the deeper you go, until eventually the material itself changes into something that has no equivalent in any laboratory on Earth. We know exactly what this descent is like, because in December 1995, we sent a probe to experience it. The Galileo atmospheric probe entered Jupiter's atmosphere on December 7th, 1995, at 170,700 kilometers per hour. The friction with the atmosphere was so violent that the temperature of the plasma ahead of the probe reached 14,000 degrees Celsius, hotter than the surface of the Sun. The probe experienced a deceleration force of 228 times the force of gravity. The heat shield lost more than half of its own mass in those opening seconds, burning away to protect the instruments inside. The probe survived, a parachute deployed, and for 58 minutes it sent back data: pressure, temperature, wind speed, cloud composition. The probe reached a depth of roughly 150 kilometers below the visible cloud tops. By that point, the atmospheric pressure had reached 22 times Earth's sea level pressure. Then silence. The probe was gone. Scientists estimate Jupiter's atmosphere continues for tens of thousands of kilometers below that point. At just 1% depth, pressure exceeds 1,000 times Earth's atmosphere. Go deeper still, and the pressure reaches 2 million times Earth's atmospheric pressure. At that point, hydrogen, the ordinary gas that makes up most of Jupiter, gets squeezed so hard that it transitions into metallic hydrogen, a material that conducts electricity like a metal while remaining fluid, something that does not exist naturally anywhere on Earth. And here is something Juno has only recently revealed. Jupiter's core is not what anyone expected. Rather than a dense, compact ball at the center, Juno's data suggests a larger, fuzzier, diluted core, a diffuse region where the boundary between core and atmosphere blurs. The inner structure of the largest planet in our solar system is still, in some fundamental ways, a mystery. Step back to the upper atmosphere, the region the Galileo probe entered before descending. Even here, the conditions are overwhelming. Jupiter's winds reach speeds of 620 kilometers per hour, 5 times the speed of the most destructive hurricane ever recorded on Earth. And these are not occasional storms that form and dissolve like weather on Earth. They are permanent features, giant rivers of gas flowing in opposite directions, hundreds of kilometers wide, and they have been there for longer than recorded human history. The Great Red Spot, the famous oval storm visible from Earth, has been continuously active for at least 350 years. It is currently about 13,000 kilometers wide, wider than the entire diameter of Earth. Juno has been mapping Jupiter's atmosphere since 2016, and what it has found is both beautiful and deeply unsettling. In January 2025, specifically on its 69th orbit, on January 28th, Juno obtained the first ever temperature measurement of Jupiter's North Polar stratospheric cap. The result? That polar region is roughly 11 degrees Celsius cooler than the surrounding atmosphere, encircled by a ring of winds exceeding 160 kilometers per hour. The cyclones at the poles, storms individually larger than the continent of Australia, have been sitting in the same positions for years, held in place by dynamics that scientists are still working to fully understand. Inside those storms, lightning fires continuously, bolts estimated to carry up to 10 times the energy of a typical lightning strike on Earth. There is no shelter anywhere in Jupiter's atmosphere, no calm pocket, no safe zone. The violence is planetary and permanent. Here is what changes the picture entirely. Everything described so far, the radiation, the pressure, the temperature, the storms, none of it is a freak occurrence. None of it is a bad day on Jupiter. This is Jupiter on a perfectly normal, quiet Tuesday. But even if all of that could be solved, even if some future technology could shield a human from the radiation, survive the atmospheric pressure, and withstand the winds, there is still one problem that has no obvious solution. Jupiter's escape velocity is 59,500 meters per second. That is the speed you need to reach to break free of Jupiter's gravity and head home. Earth's escape velocity is 11,200 meters per second. Jupiter's is more than 5 times higher. The most powerful rocket ever built, NASA's Saturn V, which sent human beings to the moon, was designed to reach Earth's escape velocity. To escape from within Jupiter's gravitational pull, you would need a rocket that produced many times more thrust, carrying fuel that itself adds weight, requiring still more fuel. The engineering mathematics of escaping Jupiter's gravity from close range do not currently work with any propulsion technology that exists or that is currently planned. Jupiter does not just make the journey there lethal, it makes the journey home almost impossible. The most honest measure of what Jupiter does to visitors is what it did to the best machine we ever sent there. The Galileo orbiter, not the probe, but the spacecraft that carried it, spent 8 years circling Jupiter. It completed 34 orbits. It gathered data about Jupiter's magnetic field, its atmosphere, its moons. It was, by any measure, one of the most successful planetary science missions in history. At the end of those 8 years, scientists made a deliberate choice. Rather than let Galileo drift uncontrolled through Jupiter's system, where it might eventually impact Europa and potentially contaminate that moon's ocean with bacteria from Earth, they aimed the spacecraft directly at Jupiter. On September 21, 2003, at 11:57 in the morning Pacific time, Galileo entered Jupiter's atmosphere at nearly 48 kilometers per second. Within 2 minutes, it was completely gone. 8 years of operation, 34 orbits, 4.6 billion kilometers traveled, gone in 2 minutes, and the planet kept going. The storms kept swirling, the radiation kept flowing. Jupiter took no notice. That same relentlessness continues today. When Juno flew close to Io on December 27, 2024, its instruments captured the most energetic volcanic eruption ever recorded on that moon. A lava field covering more than 40,000 square miles, an area larger than the state of Kentucky, erupting with a total energy output estimated at 6 times the combined output of every power plant on Earth. That eruption was still actively pouring lava into space as recently as March 2025. Io is being cooked from the inside by Jupiter's gravity. The same tidal forces that make Jupiter so impossible to escape are continuously squeezing Io's interior, generating so much heat that it has become the most volcanically active body in the solar system. So here is the full picture. To reach Jupiter, you spend over a year absorbing deep space radiation before you even arrive. Approaching the planet, you enter radiation belts delivering hundreds to thousands of rads per hour, lethal exposure measured in minutes. Its most scientifically interesting moon delivers a fatal radiation dose in under an hour on its surface. Its atmosphere has no floor, no landing point, and destroys everything that enters it. Its winds blow permanently at 620 km per hour. Its storms are wider than the Earth and older than modern civilization, and its gravity makes leaving nearly impossible with any rocket technology we have or are close to developing. Every one of those is independently lethal. Together they make Jupiter the most hostile destination a human being could choose anywhere in our solar system. And yet we have not given up on it. Juno is still there right now, still orbiting, still sending data, still being slowly worn down by radiation, doing science until the day it cannot anymore. Europa Clipper is on its way, carrying 9 precisely chosen instruments designed to tell us whether Europa's ocean, that enormous body of water hidden under miles of ice, could harbour life. And later this decade, the European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer, will follow, arriving at Jupiter in July 2031 to spend years studying Europa, Ganymede and Callisto in detail, because Jupiter is not just a place that kills things, it is a place that holds answers. About how our solar system formed, about what conditions allow planets to take shape, about whether the ingredients for life exist beyond Earth, about the physics of a world so extreme that our best instruments can only scratch the surface of it. The machines we send keep dying, and we keep sending better ones. Because what Jupiter is keeping from us might turn out to be some of the most important things we ever learn. For now, Jupiter belongs to the machines. If you want to keep exploring the most extreme places in the universe, subscribe, because there is a lot more to find.